So, in the previous parts, we went through the construction and announced the main theorem. The usefulness of our construction should be measured by its power. That is, how many new examples can we produce? So, is our work useful? Yes. Thanks to our construction, we can construct many new examples of triply periodic and singly periodic minimal surfaces. In theory, we have uncovered infinitely many new examples, but examples are not equal. Some examples provide important answers to important questions, hence they are more important than the other examples. So in this part, I will present many examples. Although our work is mostly successful, successful is boring. So I will also include some unsuccessful examples. We will first see some examples of triply periodic minimal surfaces of genus 3. I have mentioned that this is my personal major concern. This first example is not new. This is the saddle tower limit of mixed surface. The graph is represented in a flat 2 torus, which appears here as a parallelogram spanned by vectors t1 and t2. It has two vertices, four edges, and two faces. The genus of the surface is 1 plus the number of the faces, hence the genus here is 3. If one vertex is put on the vertex on the corner of the parallelogram, then the balance condition forces the other vertex to lie at the center. So the balanced graph is described by two parameters. The balanced phase function is also described by two parameters, as labeled in the picture by A and B. Plus the node opening parameter, we have 5 parameters in total, as we expected. In the bottom, you see some mixed surfaces near the saddle tower limits. They all have a horizontal reflection plane, but the phase function in the graph can actually be very flexible, and most of mixed surfaces do not have horizontal reflection plane. This is a new example of triply minimal surfaces of genus 3. So the graph is again in the torus. It has a single vertex, 3 edges, and 2 faces. Hence, again, the genus of the surface is 3. It is trivially balanced and trivially rigid. So the graph is again described by two parameters. The phase function is also trivially balanced and is described by two parameters. So together with the node opening parameter, we have again a 5-parameter family as we want. This new 5-parameter family contains two surfaces that were previously known. One is Schwarz H surface, as you see in the bottom left. The other is the rhombohedral deformation of the gyroid, as you see on the bottom right side. Previously, Matthias Weber and I have proved that H can be deformed to G, so the two can deform between them through a path of TPMS G3s, but that path must go through mixed family. This new family here, near the saddle tower limit, reveals that there is another deformation path between H and G that that is much more direct, meaning that it does not have to go through mixed family. So these two examples are not success stories. The graph is the same as that for the mixed family. So if they give rise to minimal surfaces, they would be of genus 3. In fact, we do know two examples of TPMS G3s that admit this kind of saddle tower limits. One is the tetragonal deformation of gyroid, and the other is the saddle tower limit of the OH family that Matthias Weber and me recently constructed. However, our construction is not conclusive here because the phase function is not rigid. To see this, note that if we add the same constant to parameters a and b, the new phase function again is balanced. Such a transform can be interpreted as the sliding of one saddle tower with respect to the other. However, the 3D lattice of the TPMS is not changed. So it seems that there is a one-parameter family of TPMS with the same 3D lattice. I personally do not believe this, and I did some numerical experiment. It seems that if you slide one saddle tower with respect to the other, the lattice will have a very slight horizontal deformation, but the deformation is too subtle to be perceived in the limit. So the nature of these two families is yet to be investigated. We have mentioned that we will allow parallel edges, and here are some examples. They are all of higher genus, but still very interesting because they generalize famous examples by Schoen. As we see below, these are the corresponding Schoen surfaces. In fact, allowing parallel edges significantly increase the power of our construction. Because if you have a graph that is balanced but not orientable, you can double every edge and the new graph would be still balanced but orientable now. This is another inconclusive example. This is meant to generalize Schoen's famous so-called HT surface, as you see below. The problem here is that the graph, not the phase function, the graph is not rigid. To see this, note that the graph is an arrangement of lines, and you can parallelly move a line and the graph. So, for example, you move this horizontal line to here, and the graph remain balanced. Of course, we can impose a symmetry saying that the two triangles must be identical. Then do the construction again, which would actually work, but this is not detailed in our paper. Now let us have a look at singly periodic examples. This first one is a very simple graph. It appears as an arrangement of three lines, two vertical and one horizontal. The graph is combinatorially a tree. For a tree, every edge is a cut. As a consequence, a balanced phase function must take the value 0 or pi everywhere. This is consistent with the theorem of Perez and Tercet, which says that every singly periodic minimal surface of genus 0 with Scherk ends must be symmetric in the horizontal plane. For this simple example, the phase function is supported on the single edge in the middle. So there are two ways to glue the saddle towers, as we see in the picture. So what is interesting about this example is the embeddedness, which is very delicate to determine. What happens here is that the force on the middle edge is not a unit force anymore after the desingularization. The change in the force depends on the way we glue. If the phase difference is 0, as shown in this picture, the force here will increase. Then the Scherk ends, the four Scherk ends, corresponding to the rays, vertical rays here, they must bend away from each other to balance the change of force. In this case, the surface is embedded. But if the phase difference is pi, as shown in this picture, the force in the middle will, however, decrease, and the Scherk ends, the four Scherk ends, must bend towards each other to preserve the balance. But they were parallel at the beginning, so they must have intersected each other after the bending. Hence, the surface is not embedded, as we see here. To determine the bending of Scherk ends and the embeddedness is the major concern when I glue saddle towers into singly periodic minimal surfaces in the second paper of our series. So now are two examples of it's just one example of singly periodic minimal surface with Scherk ends that is not symmetric in a horizontal plane. We have seen that to remove the horizontal reflection plane, the genus cannot be zero. So the one on the left, the triangle here, is the smallest non-symmetric example. It is actually inspired by the rhombohedral gyroid. I must point out that this is not the first non-symmetric example. There was another example constructed in 2006 by Francisco Martin and Valerio Ramos Batista, but their technique was very different. These examples are interesting because they answer a question asked by Tricet in 1996. The question was, is horizontal reflection plane necessary for all singly periodic minimal surfaces with Scherk ends? Now we know that the answer is yes if the genus is zero, but no with higher genus. Our construction is not conclusive for the one on the right side, the square here. The configuration is inspired by tetragonal gyroid, but as its triply periodic counterpart, the phase function here is not rigid, hence we cannot use the implicit function theory. We end this talk by some more simply periodic minimal surfaces with no horizontal reflection plane. So these are constructed by polygrams. Actually, we can construct at least one such example for every polygram. What we show here are for the pentagram and the octagram. So unlike previous pictures where the phase function are labeled on the edges, here we label the phase function on the vertices. And the phase differences can be recovered very easily. So that would be the end of my talk. Thank you for listening. If you are interested, here are some links. The first link is to the archive preprint for the first paper of our series. You can find many cool images of TPMSs from the website of Matthias Weber and the website of Brachus Surface Evolver. Many pictures and photos in this talk are taken from there. Thank you very much.